Hello everyone, I am Komal and today I present here my topic is about Raman Spectroscopy. So first of all, we discuss the contents. We discuss introduction of Raman Spectroscopy, then principle, then instrumentation, then how it works, its applications, advantages and limitation. So first of all, we discuss the introduction. So Raman spectroscopy was discovered by C.V. Raman in 1928. It is an analytical spectroscopic technique used to observe vibration, rotational and other low frequency modes in a system. So basically Raman spectroscopy is commonly used in physics, material science and other branches of physics to provide a fingerprint by which molecule can be identified. So when the radiation passes through the transparent medium, the species present scattered a fraction of the beam in all the directions. So Raman scattering result from the same type of quantities, vibration changed associated with IR spectra. The difference in wavelength in between the incident and scatter visible radiation correspond to wavelength in mid-IR region. Then we discuss its principle. So when monochromatic radiation is incident upon a sample, then this light will interact with the sample in some manners and it may be reflected, absorbed or scattered in some manner. It is the scattering of the radiation that occurs which gives information about molecular structure. So Raman spectroscopy or Raman is based on scattering. The sample is irradiated with a coherent source, typically a laser. Most of the radiation is elastically scattered, which is known as the Rayleigh scattering. However, a tiny fraction, approx 1 in 10 raised to power 6 photon undergoes inelastic scattering. That means Raman scattering, where photon either lose energy, Stokes line appears and gain energy, then anti-Stokes line appear. The energy shift measured in wave number, centimeter inverse, correspond to a specific molecular vibration creating a unique spectral fingerprint. So the intensity ratio of Stokes to anti-Stokes lines depend upon the population of excited vibrational states, while the Raman is independent of laser wavelength, providing bond-specific information. So then we understanding the Raman effect. So when a sample is exposed to monochromatic light in visible region, the sample absorbs light and major portion of the light is transmitted through the sample. However, a minute particle light scattered by the sample in all the directions. So one can observe the scattering at right angle at the incident beam. So the incident light has a particular frequency. If the scattered light has the same frequency as the incident light, the scattering is called Rayleigh scattering. And for around 1% of scattering is known as Raman scattering, where the incident frequency is not equal to the scattering frequency. So Raman scattering is the two photon process. So here we see the different vibrational levels and a virtual energy state. So when the monochromatic incident light interact with the electron in the sample, the electron absorb the energy from the incident photon and rise to a virtual state of energy. The energy transfer given by the formula E is equal to h mu. So mu is the frequency of the incident photon and electron fall back by losing energy if the energy loss is equal to the energy of the incident photon. Then the scattering is known as the Rayleigh scattering, where the energy of the incident photon is equal to the scattered photon. So h mu s is equal to h mu I. So this is known as Rayleigh scattering. Then sometimes electron losing energy from the virtual state and can fall back to the different vibrational level. In this case, energy lost by the electron is different than the energy absorbed from the incident photon. As a result, a photon emitted by electron has the energy different from the incident photon. This is the possible where mu s is not equal to mu I. This scattering is known as the Raman scattering, where mu s is the frequency of emitted photon. So, depending upon the final energy of the electron or final vibration level of electron, Raman scattering can be separated into two parts, Stokes and anti-Stokes. So, if mu s is less than mu I, then Stokes line appear, where electron absorbs energy, and if mu s is greater than mu I, then anti-Stokes line appear, where electron emit or lose energy. So, Raman spectroscopy also gives us a molecular fingerprint. So here we see the intensity versus frequency curve, where the Rayleigh scattering has the most intensity, and as compared to anti-Stokes, Stokes has the more intensity. So here we discuss the reason of the intensity of the Stokes line is more than the anti-Stokes line. So first of all, we discuss the Rayleigh scattering and the intensity of the Rayleigh scattering. So when the photon are incident on the sample and electron absorb energy from the ground vibrational states, it goes to the virtual state, its intermediate state, not a stable state, and goes back scattered to the ground state. So here the energy loss, there is no energy loss. The energy of the incident photon is same as the scattered photon. So the intensity of the Rayleigh scattering is more. Then we discuss about the Stokes shift. So here the ground state vibrational level, the photon incident on a source and electron absorb energy from the ground state, and it absorb energy and go to the virtual state and scattered back to the first vibration level, not the ground state. So here there is a energy loss. Then the intensity of the Stokes shift is less than the Rayleigh scattering, and then the electron loses energy and go to the excited vibrational state before the interaction, and then interaction occur and it scattered back to the lower vibrational level, and here is a increase in the energy. So there is intensity loss. So intensity of the Stokes shift is more than the anti-Stokes shift. Then we discuss the instrumentation. So here the instrumentation, first of all we discuss about laser source, sample cell, wavelength selector, radiation transducer and a computer data system. So first of all we discuss the instrumentation. So instrumentation for the modern Raman spectroscopy consists of three components. First, laser source. Second, sample illumination system. Third, suitable spectrometer. So first we discuss the source. The source used in the modern Raman spectroscopy are nearly always laser, because then high intensity is necessary to produce the Raman scattering of sufficient intensity to be measured with a reasonable signal to noise ratio, because the intensity of the Raman scattering varies as the fourth power of the frequency. Argon and krypton ion sources that emit in blue and green region of the spectrum have the advantages over the other sources. So here are some common laser sources we use for the Raman spectroscopy, and here one side are the laser type and other side are wavelength in nanometer. So first argon ions, then argon ion laser, krypton ion laser, helium neon laser, diode laser and ND yarn laser, and here these are the wavelength of these lasers. Then we discuss the second point, sample illumination system. So Raman spectroscopy work with solid sample as well as aqueous, liquid samples and gaseous samples. So first we discuss the liquid samples. So a major advantages of the sample handling in Raman spectroscopy compared with infrared arises because water is a weak Raman scatterer but a strong absorber of the infrared radiations. Thus, aqueous solution can be studied by Raman spectroscopy but not by the infrared. So this advantage is particularly important for the biological and inorganic system and in studies dealing with water pollution problems. Then we discuss the solid samples. So Raman spectra of solid sample are often acquired by filling a small cavity with the sample after it has been grounded to a fine powder. Polymer can usually be examined directly with no sample pre-treatment. Then gaseous samples. Gas are normally contained in glass tubes 1 to 2 cm in diameter and about 1 mm thick. So gases can also be sealed in small capillary tubes. Then we discuss third point, Raman spectrometer. So Raman spectrometers were similar in design and used the same type of components as the classical ultraviolet visible dispersing instruments. So most employed double grating system to minimize the species reaching the transducer photomultiplier served as transducers. Now we discuss the working of a Raman spectroscopy. So this is the laser source. So a laser source emits a monochromatic light often in the visible or near infrared region. Then the laser beam passes a series of optical filters like notch filter, long press filter and mirror. So mirror reflect the laser light toward the sample while allowing Raman scattered light to pass through, ensure that only the desired wavelength laser line reaches the sample and Rayleigh scattering light be suppressed. Then the focus laser beam interact with the sample. So Raman scattering occurs generating both the Stokes and anti-Stokes line. Raman scattering occurs, then the backscattered light from the sample contain the both Rayleigh elastic and Raman inelastic scattered light. Then the scattered light is collected by the objective lens and it is directed back through the dichroic mirror and filter to remove the Rayleigh scattered light and allowing only the Raman signals to pass. Then the filtered light pass into a spectrometer and it typically contained a diffraction grating and prism to disperse light into the component wavelengths. Then the detector, CCD detectors or similar sensor capture the dispersed Raman spectrum and the detector convert the optical signals into the electrical signal for the data processing. Then the output comes as Raman spectra. So final output is a Raman spectrum intensity versus Raman shift curve shown in the next slide. Raman spectrum basically a plot of signal intensities versus Raman shift. So Raman shift in centimeter inverse is equal to energy of photon in and for energy of the photon out. So Raman spectroscopy basically tell us about the information about a molecule structure, its composition and properties by analyzing how the light interact with its chemical bonds. It essentially creates a fingerprint of the molecule revealing details about its vibrational modes, provide detailed information about the chemical structure, phase and polymorphy, crystallinity and molecular interactions. And Raman spectroscopy graph, intensity versus frequency graph, also known as Raman spectra, and reveal the information about the vibrational modes of the molecule or crystals, and the x-axis represent the frequency or energy of the scattered light, where the y-axis represent the intensity of the scattered light. By analyzing the position and intensities of the peak in the spectrum, we can identify the chemical fingerprint of the material, its structural features, even the presence of specific functional group or defects. Then we discuss the applications. Raman spectra of inorganic species. So the Raman technique is often superior to infrared for spectroscopy investigating inorganic systems because aqueous solution can be employed. In addition, the vibrational energies of the metal bonds are in the range of 100 to 700 centimeter inverse, a reason of the infrared and experimentally difficult to study. So these vibrations are frequently Raman active. However, peaks with AV values in the range are readily observed, and the Raman studied are potentially useful sources of information concerning the composition, structures, and stability of the coordination compounds. Then Raman spectra of organic species. So Raman spectra are similar to infrared spectra in that they have regions that are useful for functional group detection and fingerprint regions that permit the identification of specific compounds. Raman spectra yield more information about certain type of organic compounds than do their infrared counterparts. Then quantitative applications. Raman spectra tend to be less cluttered with peaks than infrared spectra. As the consequences, peak overlap in mixture is less likely and quantitative measurements are simpler. In addition, Raman sampling devices are not subject to attack by moisture and small amount of water in a sample do not interfere. Then biological applications of Raman spectroscopy. So Raman spectroscopy has been applied widely for the study of biological systems. The advantages of this technique include the small samples requirement, the minimal sensitivity towards interference with the spectral details, and the conformational and environmental sensitivity. And Raman spectroscopy also used in biology, chemistry, physics, astronomy, and material science. Then we discuss the advantages and limitation of Raman spectroscopy. So, Raman spectroscopy is a non-destructive technique, means no sample damage in this technique, and minimal sample preparation is required, and it works with aqueous solution, liquid solution, as well as gaseous and solid solution, and it has excellent spatial resolutions, and it provides the molecular fingerprint of the molecules. And its limitation is it has very weak signal, low sensitivity, and sometimes fluorescence interference common. And it has an expensive instrumentation, and not all the vibration are Raman actives, and lasers sometimes damage the sensitive surfaces. And it's all about the Raman spectroscopy. Thank you.